All right, so this is going to be a really quick review of dilations. The only thing that's going to be a little bit new is I'm going to go ahead and compare that to something called similarity, but they're pretty much the same thing, just different words. So dilations from a while back, basically like you're talking about middle school is when you should have learned this. You're really just when you make a figure or a shape either bigger or smaller, right? You enlarge it or you just make it smaller. Now, one of the most important things you're going to have to know is scale factor. Scale factor is basically you're saying, I'm going to make this shape, 2 times as big or half as big or, something like that. The rules for it is pretty obvious, right? Like, if the scale factor, so if we say, if the scale factor is greater than 1, then you're obviously making an enlargement. So you're going to enlarge the shape. But if it's less than 1, then you're going to just make it smaller, right? And that's a little bit, intuitive, but there you go. Let's see. When a figure is dilated, all of the angles remain the same. So this is also super important, right? You cannot change the angles. All you are changing is basically like the side lengths. The angles have to be the same, and based off of that is also how we're gonna sort of write relationships. So you just got to be careful with that. And then the last one, pretty much, it's just the understanding the scale factor. When a figure is dilated, all the side lengths are multiplied by the scale factor. So if you know what the scale factor is, if you can figure it out, which I will show you how to, then you just have to apply it to every single side. One of the important things for this section, though, is knowing which direction you're going into, right? So basically, like, if your two figures, one is smaller than the other one, are you going from, small to big, or are you going to do big to small? So the direction, it's extremely important for you to be able to understand that and apply it. Okay, so let's go ahead to just a little bit more definitions, and this is where sort of the new thing comes into play, right? Something called similarity. Everything I just talked about dilations, it's similarity. So if two figures has a scale factor and all the angles remain the same, then we say that they are similar. And the notation for similarity is like this little squiggly line here, which looks really bad here, but it's just a little squiggly line between the name of the two shapes that you're talking about. You could either be talking about like triangle, ABC is similar to a different triangle, right? DEF. Or you could even be talking about like a square. I would just put a square there, blah, 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 is similar to blah, right? So that's basically the notation for it. But once again, if you understand dilation and the definition for it, it's the same thing. It's just the word is similarity now. So looking at these two, are the following figures similar? So there's two things that you always need to basically like check off, right? You need to check off, does it have a scale factor? Right, that's one of the things. And then are the angles congruent based off of being in the same spot? You're not talking about like rotating it or and then changing where it's at. We'll get to those more complicated examples later. But for right now, so let's look at the sides. So you have 10, 6, and 7, and then you have 20, 12, and 14. Right now, you can really tell, like, hey, what's the scale factor? Like, what did you multiply it with? But remember, it's really important to know which direction you're going. Okay, so the direction. I'm going to show you both ways just so you can get the hang of it, but it's most of us usually tend to go from small to big, but whatever. So let's go small to big. And we know this one is the small one just because obviously look at the side lengths, they're smaller numbers. So now you're basically, this is sort of like a step a lot of people take for granted, but taking it back to basics, you're trying to match the sides, okay? So if you notice, A has one little tick mark, D has one little tick mark, B has 2 tick marks, and E has 2 tick marks. So what that means is that this side is basically like those two sides, they're called corresponding, I think. And so we look at the two numbers, right? We're going from 10 to 20. So how do you go from 10 to 20? Using multiplication. Remember, scale factor is all about multiplication. We're multiplying by 2. So technically that right there is my scale factor, okay? And then we can check, does the scale factor actually work for all the sides? So once again, we look at the angles, right? Just to get it to match. So 2 tick marks there. 3 tick marks, 3 tick marks. So then that means this side is going to be corresponding to that side. And then we just look at our numbers. 6 and 12. Does it have the same exact scale factor? Which it does because it's times 2. And then the last one, 7 and 14, is pretty obvious. Now, if you cannot figure out this times 2, just, for whatever reason, what we can do is we can create something called proportions, where you're basically just creating like fractions and you're saying, do we get the same fraction? So I'm going to go ahead and do that right now. But the most important part is you have to match the sides correctly. So I'm going to do 10 and 20 first, because since that's the first side I did. So 10 and 20, what I can do is I can do this right there. 10 divided by 20. Notice how I put the 10 on the top. So what that means is if I want to compare the 6 and the 12, I'll do it like this, where the 6 is also on the top because it comes from the smaller triangle. So you can either write it like this, or you can go ahead and do the reciprocal. That'll be the same. That'll give you the same answer, which yes, they are similar, but it won't give you the same exact numbers. But so let me go ahead and finish this one off. And so the last sides are 7 and 14. Okay. And so what ends up happening is you're going to simplify these and you're going to end up with a decimal. And this one here is going to be equal to 0.5. And every single one of them is 0.5. So what this means here is that this is the scale factor, but it's the scale factor to go from big to small. Because if you notice, 0.5 is less than 1. And by definition, that means you're sort of, you're making something smaller. So if I were to go ahead and do my arrow like this, it would actually be times 0.5. Right, so already notice the two different types of arrows. Let me go ahead and erase that so it could look nicer. So when I went from small to big, right, I can see that it's times 2. But when I go from big to small, it's going to be 0.5, and that's just because of the other fraction. Now, for those of you that want to, or you care about it, in order for me to get the 2, I would just flip-flop all of these fractions. So for instance, if I do 20 divided by 10, that's equal to 2. And then I can go ahead and do 12 divided by 6, that's equal to 2. And then I'll do 14 divided by 7. Okay, so if you notice, this here is the scale factor from small to big. Okay, but it has to be the exact same number. This was 2, 2, 2. This one over here was 0.5, 0.5, 0.5. It has to be the same number. Okay, if your fractions are in the correct order. So my last thing that I'm going to do is I'm going to go ahead and just write the actual final answer. So let me make some space here. And are the following figures similar? It's yes, because of the scale factors. You can decide to choose whichever one. And then the last thing I'm going to go ahead and do is write the similarity notation. So yes, I can say triangle. And this is where it is up to you how you want to write it. I'm going to go ahead and say ABC is similar to triangle, but now it's super important. I chose to use A first and then go to B and then go to C. So I need to look at the triangles. So I chose to start at A, so that means I have to start at D. And then I chose to go up to B that has 2 tick marks, so that means I have to go to the one that has 2 tick marks. So it'd be DE, and then I ended at the C with 3, and so that means I need to end the F. This part right here is going to be extremely important, right, once you guys get to more difficult problems. But that is really just the basis of similarity and dilations when we're talking about, like, the question is, are they similar? Okay, so let's go ahead to the next example. I'm pretty sure you're able to figure this out super quickly, right? Based on the definitions of dilations, are these figures dilations of each other, right? So the question's changed. I'm using the word dilation now, but remember, it's still talking about the same exact thing. Does it have a scale factor? Is it the same scale factor? And so all we have to do is go ahead and compare the sides accordingly. So let's see. 1 and 2 tick marks, so I have to do 1 and 2 tick marks there. So that means I went, depending on how you're looking at it, from 1 to 4 or from 4 to 1. So let's go ahead and let's do small to big. So if I go small to big and I start at 1 and I end up at 4, that means I multiplied by 4. Okay? And so now what I just need to do is check every single side length and is it the same thing. So I'll do these two right here and these two right here. So if I go ahead and I do 1.5 to 3, that scale factor is actually going to be times 2. So if you notice, scale factors are different. What this means is that these are not dilations, right? It is not a dilation. One is not a dilation of the other one. You can do this either the scale factor way, or like from the other example, we can create our proportions, which is what I'm going to do right now. So I'm going to go ahead and do, I'm going to compare sides. 1 to 4, 1.5 to 3, 3 to 6, and then 4 to 8. Okay, so this one is equal to 0 0.5, this one is equal to 0 0.5, 0 0.5, 0 0.25. Just because this one is not the same, that means automatically, right, we can say not dilation. We can even go ahead and take it one step further, and we can say not similar. Okay, because there you go. If you were to flip them, right, all of them would be equal to 2, except for this one here, which would be equal to 4. But the whole point is it is not the exact same number. All right, so let's go ahead to the next one. Are these shapes similar? We see one of the shapes sort of like rotated a little bit, but that's okay. We can go ahead and match the sides. Okay, so 5.5 is going to be matched to this one because that's where I started at the 78, go to 48, 78, go to 48. Okay, so what that means is that I'm going to compare those two, right? So doesn't matter what direction you're going, right? Or it could be this one. You just have to understand what the scale factor is trying to say. So I'm going to go ahead and do 5.5 divided by 9. And I can already tell that this is going to be a decimal. Or I can go decimal smaller than 1. And then, or I can go ahead and do the other one, which again, I know this is going to be a decimal, but this one's obviously going to be bigger than 1, and this one's going to be smaller than 1. You're always going to have that because, it depends on which direction you're going. Okay. And so going ahead and dividing those numbers, I get 0.6111, the little bar on top or whatever, and then we get 1.63 with the little bar again on top. All right, so just understanding the difference between them, right? This one here, the one that's less than 1, this would be the scale factor for going from the big shape to the small shape. 1.63, that is the scale factor from going from the small shape to the big shape. Okay, so now there you go. We can go ahead and now compare the other side and see, do we get the exact same scale factors? Okay, so 2 and 3, once again, they have to be in the sort of same order in order to compare the numbers. Okay, so in order to compare the 0.613, the number that I'm actually, or the fraction, sorry, that I'm actually going to compare is 2 divided by 3, because the smaller number is the one that, the smaller shape is the one that I'm using the numerator, and then the bigger shape is the one I'm using the one for the denominator. And then for the other one, it's basically just flip-flop, so 3 divided by 2. So I can go ahead, and this one is going to be equal to 0.66, and then this one is going to be equal to 1.5. And so now what we can do is compare these two numbers, right? This one compared to this one, and if we notice, they are not the same. And then also we can go ahead and do the other one, 1.63, comparing that to 1.5. So what does this mean is just that they are not similar, right? So not similar. You can say similar, or you can write the little notation. It's really up to you. Okay, so let's go to the next example. For this next example, it's a little bit interesting because you have no shape, so you really have to read and be very careful with it. So you have two figures, and so there is a scale factor. So it does have a scale factor. It's actually equal to 1, which is a little bit different. We haven't talked about it. And then all of their corresponding angles are congruent. So if you recall, there's two things that you need, right? You need a scale factor, and it needs to be the same for all sides, which it's basically giving it to us right here. And then you need the angles to be congruent when we're talking about corresponding sides. And that's the second part. So just based off of those two, are the figures similar? Yes. Now, some of you might be a little confused with it. Like, how can they be similar? Well, let's just think about like a triangle, right? With sides 5, 5, and then let's see, if you paid attention to the other videos with the, does it form a triangle? I have to be careful here. Let's go ahead and do 6, okay? So 5 and 6, 11, yeah, all right. It's basically saying, we take this shape and then we multiply it by 1 and we create a new shape with different letters, right? A, B, C, and then let's do, I don't know, D, Z, T, whatever, right? Just to be different. And this one's going to equal to 5, 5, 6. Since these two are different figures, we can actually say that they are similar because the scale factor is 1. It's okay for the scale factor to be 1. It doesn't enlarge it or make it smaller. It just basically it's like copy and paste, if you really want to think of it like that. Okay, so let's go ahead to the next example. Are these figures similar, right? You can look at the sides, compare the sides. Because of the shape of the figure, it's a little easy to compare sides. BC is going to be corresponding to XY. We can say WZ is corresponding to AD. We can say that BA is corresponding to that one, XW, and then CD is corresponding to that one. And then if we just start comparing all the sides, right, let's go ahead. 15 to 150. What would be the scale factor for that one going in the direction of the arrow that I drew? It'd be times 10. For going to the 40, again, it'd be times 10. And if you notice, all of them are actually going to be times 10 going from small to big. So are the figures similar? Yes, they are similar. Okay. Let's go ahead to the next example. Now this one here is where you really start thinking about basic definitions and just applying it to other problems. I mean, you can say they're higher level, but it really depends. So the first one is talking about circles. So definition of a circle, right? So a collection of points that is equidistant, right, from another point, which ends up being the center. And then all of these distances, we can categorize them as R for radius, right? And we know that the R is the same for all of them. So let's imagine we have two circles, right? With the first radius, let's call it 4. And then the next radius, let's call it, I don't know, whatever you want, like 12. Are these circles similar? So let's think about the definition. Does it have a scale factor? Can I multiply? I know this one doesn't have sides, but technically the radius. Can I multiply the radius to become the other circle? And we can, because then it'll just be a scale factor of 3. And now, are the angles the same? Well, we're talking about a circle, and so when you go around, 360, 360. So therefore, these are similar. Same thing now, but for squares. You have to just think about what is the definition of a square, right? Square has 4 congruent sides, and all of the angles are 90 degrees. So let's imagine you take one square with side length 10, and then you take another square with side length, let's do, I don't know, 3. Are these two similar? Well, they definitely have the angles being congruent in both shapes because they're all 90. Now we have to see, is there a scale factor? Well, if you really think about it, you go from 10 to 3 by multiplying it by 0 point something. And it's going to be the exact same thing for all the other sides, right? Because we're talking about squares. So therefore, these are similar as well. The last one is talking about rectangles. So let me go ahead and draw 2 rectangles, and then let's see, right? Let's imagine really basic. We have sides 1 and then side 3. I'm going to go ahead and do this. And then for this other rectangle, we have sides, I don't know, 4, and we have sides, let's do 9. The numbers I chose were very specific, but it's really easy to prove something is wrong or, disprove something just because you need one example. And so then I'm going to go ahead. This one is congruent to this one, but I've already used 1 and 2 tick marks. So I'm going to use 3, and then 1, 2, 3, 4, 1, 2, 3, 4. Okay. So just so you know, 9, 9, and then 4, 4. So if we compare sides, right, we could go 1 to 4, which means it has a scale factor of times 4 going in that direction. But then if we look at the 3 and 9, that actually has a scale factor of times 3. So right there, it will not work. Now, we did have all the angles congruent, by the way, because in a rectangle, right, it's always equal to 90, all of them. So I just wanted you to know that, right? Like, it did half of it, but it didn't do enough. So are all the rectangles similar? No, not all rectangles similar. So really quick recap of dilations and an intro to similarity for this one.